This is the second of our lessons on time. In the last one, we looked at Kepler's laws and the definitions of a day and a year. Kepler's first law is that the orbit of each planet is an ellipse, with the Sun at one of the foci. In the last lesson, we exaggerated the amount of ellipticity in our diagrams in order to make this point clear. But in fact, the difference in distance between perihelion and aphelion is only about 3% of the average Earth-Sun distance over the year. The Earth's orbit is almost circular, so the difference in distance at summer and winter has very little effect on the climate. In the northern hemisphere, early January can be one of the coldest times of the year, but this is at perihelion, the time when the Earth is closest to the Sun. So, as we suggested in the last lesson, the changes in the seasons must be caused by something else. The actual reason is the tilt of the Earth. All of the 8 major planets orbit in concentric ellipses very close to the same plane. For the Earth, this is called the plane of the ecliptic. However, the axes on which they spin are different. For instance, Mars is at 25 degrees off the perpendicular, Uranus is 98 degrees off, and Venus is nearly 180 degrees off. Earth is 23.5 degrees off the perpendicular of its ecliptic. This is what causes the annual changes in the seasons and the hours of daylight over the year. If we imagine the line between the centre of the Earth and the equator being extended out into space, we get another plane. This plane is called the equinoctial, and it is perpendicular to the Earth's spin axis. The angle between the ecliptic and the equinoctial is also 23.5 degrees. This is sometimes called the obliquity of the ecliptic. If this angle is 23.5 degrees, then the angle between the Earth's spin axis and the ecliptic must be 66.5 degrees. It is not that the Earth's actual tilt in space changes over the year. For instance, this is the situation on the 21st of June. The Earth's axis is inclined at 23.5 degrees to the ecliptic. This points to some fixed point in space, very close to Polaris, which can be taken as being fixed in space over a period as short as a year. 6 months later, the orientation of the Earth in space has not changed. It is still pointing to the same place in space near Polaris. What has changed, however, is its orientation relative to the Sun. In June, the line between the Sun and the centre of the Earth passes through latitude 23.5 degrees north. 6 months later, the line between the Sun and the centre of the Earth passes through latitude 23.5 degrees south. Over the year, the latitude directly under the Sun changes from 23.5 degrees north to the equator to 23.5 degrees south to the equator again and back to 23.5 degrees north. If we look at it from an Earth-centred point of view, this is the apparent path of the Sun's overhead during the year. In order to define points in space, we need a celestial reference system similar to latitude and longitude. With latitude, we take the equator as the reference and measure the elevation angle to some point on the Earth's surface. For celestial measurement, we imagine the equator expanded out into space to form the equinoctial, and again measure the elevation angle to some point in space. This angle, which is the celestial equivalent of latitude, is called declination. Declination is the angle measured northwards or southwards from the equinoctial to a line joining the centre of the Earth to a body in space. It is the annual change of declination which causes the seasonal temperature changes. Let's consider the Earth on June the 21st. The Sun's diameter is more than 100 times greater than the Earth's. Therefore, relative to the Earth, the Sun's rays arrive on a broad front. Imagine a square cross-section of this heat and light, with sides of, say, 1,000 nautical miles, and another one down here. Each of these cross-sectional areas in space contains the same amount of heat. However, the angle at which the heat meets the Earth at latitude 23 north means that the heat is concentrated over the smallest possible area. At 23½ south, it is spread over a much larger area, and so the heat is less concentrated. The Earth is rotating about its axis, which is tilted with respect to the Sun's rays, so that the area of heating remains at the same latitude over a day. This situation represents a northern hemisphere summer or a southern hemisphere winter. 6 months later, the Earth is at the opposite end of its orbit, and so the Sun is directly over latitude 23½ south. This gives us a southern hemisphere summer or a northern hemisphere winter. The latitude corresponding to the Sun's maximum northerly declination is 23½ north. It is known as the Tropic of Cancer. Similarly, the latitude corresponding to the Sun's maximum southerly declination is 23½ south. It is known as the Tropic of Capricorn. The regions of the Earth between these two latitudes are called the tropics, or the tropical zone, and they are the hottest parts of the Earth. The annual change of declination also causes the seasonal variation in the length of the hours of daylight. Again, consider the Earth on June the 21st. We'll take two positions on the Greenwich meridian, both experiencing local noon. One is at the equator, and the other at 40 north. The Earth now rotates for 6 hours, so that the local time for each of them is 6 p.m. You can see that the position at the equator is passing into darkness. However, the position at 40 north is still in daylight because of the inclination of the Earth. The Earth will have to rotate for another 1½ hours before this point passes into darkness, when the local time is 7:30 in the evening. This is a northern hemisphere summer, when the daylight hours are longer. However, for the southern hemisphere, it is winter. Their daylight hours are shorter. Here, the Earth has to rotate until only just after 4:30 in the evening for it to pass into darkness. 6 months later, the situation is reversed. You can see that the hours of daylight are now longer in the southern hemisphere. For them, it is summer, whilst the northern hemisphere has its winter. One of the consequences of these changes in declination is the phenomenon of midnight sun at high latitudes at certain times of the year. Consider the latitude of 66½ degrees north on June the 21st. The meridian facing the Sun is experiencing local noon. Local midnight occurs at its anti-meridian. Everywhere north of this latitude is in sunlight for a whole day. Similarly, everywhere south of 66½ degrees south is in darkness for a whole day. Higher latitudes give longer periods of continuous light or dark, but 66½ degrees north and south are the lowest latitudes at which it is possible to get at least one day of continuous light or of continuous dark, depending on whether it is summer or winter. They are therefore called the Arctic Circle and the Antarctic Circle.